Uh, with no further ado, Brad Nelson, introduce yourself, Brad, and tell us what you're going to talk about.
I am Brad Nelson, and I'm going to talk about µEforth and my efforts to add fault handling to it, and a bunch of background on that. So let's get to it. So so what is fault handling? What I mean by fault handling, actually, it actually can be confusing because people use this term for a bunch of different things. But what I mean by fault handling is the idea that I want to intercept when somebody is reading an illegal address or writing an illegal address or executing an illegal address or doing something like dividing by zero, or possibly when the user has taken some action like a control break that's meant to indicate that something should stop. And by illegal, what I mean is things like unmapped memory or memory with the wrong, that you're trying to write to that you should only be able to read from with the wrong permission. Or on some architectures, this can mean things like unaligned memory. So you read something at an address that's not a multiple of the alignment of the CPU. Some CPUs will trap for that. And on a chip like the ESP32, when this happens, the default behavior is that they actually have this hardware panic that they call a guru meditation error, which is apparently some obscure reference to a type of error that was on an Amiga. Apparently, there's some long story about an early input device that you could balance on and so forth. But regardless, my goal for µEforth is to turn this into a regular fourth exception. And the reason for that is just that makes life a lot simpler. If failures that happen, even fairly low-level failures, if there's something that I can recover from, I want to be able to transform that into something that can be operated on at the level of fourth. And so, for example, if I had, say, this word evil that reads from a null pointer or some other invalid address, if I had some other word that then uses fourth exceptions, does catch and invokes evil, I'd like to be able to intercept it and make sure that I get some kind of exception code instead of the program crashing. And so concretely, the kinds of things I want to be able to handle are reading a bad address, writing a bad address, calling a bad address, dividing by zero. And ideally, I want it to apply even to failures that happen outside of fourth. So if I call into some library and or some system call and I pass in a null pointer or an invalid address, I'd like that to be something where fourth gets control back so that I don't bring the whole thing crashing down. There are some alternatives, and I thought about some of these for a while. It is possible to instrument your loads and stores in fourth and make them sort of do some checking. That can be expensive if you do it all the time. You could imagine having sort of two modes where maybe you turn on checking. Another option, Dr. Ting did this in a bunch of his µEforth variants, is to have the address space be closed. He would actually have a sort of a separate address space for a virtual address space for the µEforth machine, and then accesses were in there, and then you actually would use a special peek and poke word to actually reach out to the outside system. So you sort of know when you're dealing with dangerous memory, but most of the time you're dealing with undangerous memory. He also had would do the trick of having stacks that wrap around so that you keep the stacks in some kind of a reasonable location. But anyways, I'm going to pursue fault handling, and so two parts to this. One is that you have to be able to intercept the fault. You have to be able to, notice when something bad happens. And then when it happens, you want to be able to resume safely back to someplace safe. You want to be able to get the forth interpreter back into a self-consistent state. So the theory of this is tricky, and it actually is something that a lot of different operating systems have tried different kinds of philosophies about how to approach it. At hardware level, these things are like interrupts. You've got some kind of an event that happens that the hardware can intercept, and it will jump to an interrupt handler. And typically there's sometimes special instructions. You have to be careful about stashing away the full state of the system. And this tends to be a little bit challenging for high-level languages. You tend to end up having to have sort of either special care in terms of you can't call the usual set of things that you would call when you're in one of these handlers, or you may have to use constructs that indicate that, well, okay, I'm in an interrupt handler, so something special needs to happen. And you can have problems like if you've got global structures, they could end up in a bad state. You may be operating on a stack that something has gone wrong with it. And now if you make assumptions about what's safe to access on that stack, if there's pointers on that stack, it can be dangerous. And so, even in C, this is hard. But with Forth, we've got a reasonable pattern for doing this. It also helps that in µEforth, I'm not using the actual system call stack, so I've got the Forth stacks kind of off to one side. But I think the real challenge here is, and the reason that there's so many different interfaces for fault interceptions on each of the operating systems that are out there, is that coming up with a high-level goal for what is essentially interrupt handling is hard. You want to have the flexibility to be able to resume when something bad has gone wrong, but you still want to allow normal code to be used. You want things to sort of work as if the full set of abstractions of the language are available. And so those are kind of in tension, because if something catastrophic has happened, if the invariants of your programming language have been violated, you touched memory that wasn't supposed to be touched, something is in an inconsistent state, it isn't necessarily obvious that you can use normal code. And if you add in concurrency, things get really tricky. And so some of the approaches that have existed, things like signals, for example, we'll talk about in a moment, are sort of work when we're thinking about just whole processes, but threads can sort of monkey things up a bit. So different approaches on different platforms. µEforth runs in a bunch of different, it runs in Linux, Windows, and then a bunch of different ESP32 variants, where it's known as ESP32 Forth. On Linux, I've looked at signals, and as we'll talk about with Windows, I used a thing called structured exception handling. And then this is sort of a buildup, because the real challenge is that ESP32, I wasn't even initially certain that I could do fault handling. There's actually not a lot of documentation to support this, and there's a little miniature journey in there I'll talk about. So I started with Linux because I figured I had to make this work somewhere before ESP32, and there it's simple. There's sort of two APIs for signals. There's the classic signal interface, and then there's the more modern SIG action interface. The old signal interface is very straightforward. You have some handler that you want to create. It takes as a parameter the signal that was actually received, and then you just indicate that for a particular signal number, here's the handler, and that handler gets called. The problem is that this falls down in the face of threads. This doesn't have a lot of configurability. It can also have issues if you want to do things like have the exception be handled on a different stack than the one that the fault actually happened on. And so there's this more elaborate interface, SIG action, that lets you specify handlers, but there's also some options for flags and masks and restoring the system, and then an affordance to set up an alternate stack. So I used the second interface mainly because there's a couple of options that are useful with it. And then what about resuming to fourth? Well, the main things you'd have to do are restore the fourth registers. If you're sort of in the middle of a call to something else, you need to get back to where things are. Fortunately for sort of the fourth virtual machine registers, you can get that out of the traditional µEforth style exceptions, because what you end up having is a linked list of the state that you need to restore. But you also have to get the CPU instructions sort of back into gear. So if you're outside of the interior of the fourth interpreter, you need to sort of get back into next and resume in that way. So traditional exceptions are typically implemented like this, and this is actually this is the implementation in µEforth. It's very similar to the one in µEforth, and I think even in some other implementations that I've seen at various points. And the only sort of µEforthism is that there's a floating point stack, a single precision floating point stack, and it gets stored. The stack pointer to that stack gets stored in the exception chain. And the way this works, sort of to think about it, is you've got this variable handler, and handler is a link to the next restore point in the stack, and this is all stored on the return stack. So there's a link to the next link in the chain, the next handler, and then there's the stack pointer, the data stack pointer, and the float stack pointer. And so you're able to kind of unwind the return stack and find each point. And unlike there are some languages that do unwinding where they're very sophisticated about being able to kind of have this unwind logic, figure out the exact right handler to land on. With Forth, it's very straightforward. You just assume that whenever you throw, you catch at the next layer up, and at least take that opportunity to resume there. And so µEforth is implemented in C, and so the main sort of adjustment that needed to be made is I needed to have a system variable that's visible to both C and to the fourth interpreter to keep track of what the throw handler is, and implement the same logic that happens when you do a throw inline in C. I'm able to reuse unpark, which is this macro that is actually also used to enter the fourth interpreter, and sort of there's a park that lets you exit it, and this is used whenever you sort of yield all the way back out to the system. And then the problem you have is, okay, you found yourself intercepting this fault. How do you get back into the fourth interpreter? So how do you go anywhere? Well, in C, there's this classic old API, set jump and long jump, and this is the although there are go-tos in C, the go-to is within the current function, and so this is a sort of a global go-to. So you're able to use set jump to store a snapshot of all of the registers in a thing that's called a jump buffer, and then the first time you do this, it just stores them, and then execution continues, and set jump returns 0. And then the second time that if you later realize that you want to jump back to that point, you can call long jump with a value, and then it will resume back with all the registers sort of as they were, except that now set jump returns the value that you specified. So this lets you kind of jump back to where you were. And so grafting this into the fourth, the inner interpreter in µEforth is pretty straightforward. Here's sort of the top of it. There's a bunch of macro magic, which I'm not going to belabor, but fundamentally, there's two places that I had to make a small tweak. I needed to, inside of this conditional at the front, this init RP is the initialization code. So the first time that you kind of call into the fourth inner interpreter, I need to set up a bunch of signal handlers, and then later, every time that I enter the fourth interpreter, sort of that first call to next in front of it, I need to call set jump. And so these are the 2 points, sort of setup, and then later sort of noting the stack as it was when entering the fourth interpreter. And so this entry point is just a call to set jump that later on, if set jump returns true, it means you know you're restoring. So that's your moment to throw the signal. And then in the signal handler, I look at the signal that's received, and I need to translate this. And actually, I gave an earlier version of this presentation to the Forth 2020 group, and at that time I hadn't used standard µEforth throw numbers, and so this is the spot where I do a translation of to those, and so you get like a 9 if you do an illegal memory access, a -9. And then you need to do a couple of other things. You need to restore the signal mask so that if there's another fault, you'll resume, and then you long jump back out. And then it's just a matter of registering this handler for a bunch of different signal types. The signal types that I've registered for are memory violation, an alignment violation, although actually that doesn't actually happen on x86. So in theory, I don't believe you can actually get this one in practice. Maybe if you compile it on, there's probably some variants of Linux you could turn this on for. And then SIG int, which is if you terminate the program with Control-C. And then confusingly, the floating point exception signal in Unix it dates back to an era when they actually would throw for floating point errors, but modern floating point doesn't do that. It returns not a number and keeps computing, whereas integer computations will actually throw and use the signal. So I'm able to intercept all of those. So that's Linux. Windows is a different fish, and here Windows has a specific mechanism that they use for exceptions called structured exception handling, and it's actually a kind of an OS level notion of what exception handling looks like, and it looks a lot like sort of C++ exception handling with a try and a catch, and but then a finally, which is a thing you'll see in languages like Java and so on. But unlike sort of the native implementations of these, it is in principle at least set up to be able to handle even low-level failures and translate them into this. And so even if you get an illegal memory access, you'll happily kind of go up the exception stack with these. And so it looks like this. You could do a try. And then a critical trick that this exception handling mechanism uses is that in the accept clause, or the accept statement, there's an expression, and that expression is evaluated first before you even kind of go into the handler, and it's used to decide how to resolve that conflict of okay, I've got a fault that's happened. I could unravel the stack, but maybe I want to resume, right? And so the three options are: you can either continue with execution and just sort of ignore the failure. You can walk up the stack further, or you can actually go ahead and handle. You can call this handler. And so it's that last one that I use. Again, here's the Forth interpreter for the Windows version. It has a couple of quirks to work around some limitations. Different place that I do initialization for this one. Or rather, sorry, for this exception handler, I don't actually have to do initialization because I'm able to have a try and accept block wrapped around the whole Forth interpreter. And so if anything inside of it throws, I'm able to resume at this exception point and then do a switch statement to convert the exceptions into standard µEforth exception numbers. So that was actually all in some ways straightforward and even maybe nicer than on Linux. It's implicitly thread safe, whereas I had to play some games with thread local variables to make the Linux one thread safe. But control break proved to be a bit of a trick. So I'm using the Windows console as the console for µEforth, and what happens is that if you can register a handler for control break, but if you do anything to reinitialize the terminal, and unfortunately I do that in Forth, it will get reset. So I ended up needing to make sure that I register my handler not in the entry at the very beginning of the Forth interpreter starting, but rather only after Forth has gotten booted up. And so actually, if anything crashes in those early stages, this fault handler actually can't trigger because it isn't registered until it's sort of spun up enough to have the console there. And then the other wrinkle is that this control break, control C trigger handler is actually called on a separate thread. So if you hit control C, it's not actually, it suspends the thread that actually has the fault, and then actually does the handler in a different thread. And that's actually better hygiene, because it means that if you're trying to analyze something that happened on the fault, if you try to handle it all on the thread that failed, you could actually run into some issues. But it makes things harder because I had an implementation with structured exception handling that works just fine back on the other thread. So my clever hack for this is how do I move this back to the main thread? Well, I just crash it. And so what I do is I have a setup operation, and then some state to store, and then when I actually set things up, I go ahead and I keep track of enough information about the place where I want to resume, that I know the stack pointer and the base pointer for those areas. And then when I actually detect a control break event, I go ahead and suspend the other thread, resuspend it, because I have to make sure that it's sort of fully parked. And then I go ahead and I monkey with its stack pointer and its base pointer and then set its instruction pointer to 0. So I have it jump to address 0 after having made sure that it at least has a stack that looks like it's on the 4th stack. And so the combination of these two things means that it's sort of safely able to get back to the structured exception handling, and simultaneously that it thinks that it's seen a fault. So from the point of view of the main 4th thread, if I hit Control C, it's as if I've done a jump to address 0. And so that's my fix for that. So ESP32 for this proved harder. So ESP32 has a panic handler, and if you've ever done anything with an ESP32 of any depth, you almost certainly have seen those guru meditation errors and so on. And it triggers for most things. If you access a null pointer, if you even if you do things like the watchdog timer expires, if you have an infinite loop, it will trigger. But there didn't seem to be any documented knobs for exception handling, except for there is some documentation for a stub for GDB to be a remote debugger, but that's a fairly specific hook, and it assumes that you have some external pins connected to the device. So that wasn't going to do. And remember, there's two different kinds of ESP32. There's Extensa-based, the original ESP32s, and this is the S2 and S3. And there's also now some RISC-V5 ESP32s. So there's sort of a separate kettle of fish, and I'll briefly touch on the other one. But for Extensa, it turns out that normally I would have thought this would be in the hardware manual, but it turns out it's actually in the instruction set manual. There's a mention of a user exception vector. And so there's some implication that the hardware could do this, and so this sent me on a journey. It wasn't documented in any of the sort of ESP32 level documents. And so as I presented a bit ago, I have now a disassembler for ESP32. So I went spelunking in the code and sort of tracing, use this both to sort of examine memory, but also to figure out what would happen if I monkeyed around with certain things. And I quickly found that there actually is there is some documentation that the embedder of an Extensa chip can choose some address at which to park a set of exception handlers. And one hint that I had that this was possible is that the Extensa uses a windowed architecture. So you have a window of registers, and whenever you enter or exit a function call, you can sort of slide this window, but there's a finite number of actual registers on the CPU, and then at some point you get to the end of that stack, and it actually will flush some of the stack out to external memory, and then sort of slide the window over. And so I knew that there were handlers for that. Well, it turns out that in a fairly regular pattern, there are a bunch of different exception handlers, and down at the bottom, there's this user exception vector. And so I monkeyed around with, well, what happens if I clobber that user exception handling vector? And it turns out if you do that, then you don't get the usual panics, and instead you eventually fail due to the watchdog timer. And so I realized, well, okay, if I, I'm clearly on the right track. I was able to change the crash behavior, and so I then resorted to pulling out the source code for the low-level ESP32 system image. Some parts of it are open sourced, some parts of it are not. And so I sort of, a combination of the disassembler and the source code sort of trace things backwards. And so this user exception vector calls a function called xt user exception. It examines this register in the system that's there to record why a fault has happened. And then I thought initially that it dispatches to this load store handler, but it turns out that actually is just to decode more detail about the failure. So the exception handling logic on the chip is fairly simple, and so if there's an illegal access, it has a little bit of code that goes and tries to decode the instructions it was executing at the time to figure out which of them, which type of failure was at play. And then it comes back to that other handler, and then it actually eventually dispatches through a table. And so there's a table based on the cause, and it turns out that you can actually set the things in that table. And lo and behold, after I got to this point, I realized, wait a minute, I looked for anybody else that was writing to the table, and there's an external symbol that is actually a symbol that you can link against from Arduino, even from an Arduino build, and you can actually register your own handler. So it's documented in the source code. There's a little bit of a comment around it. It's at least an external symbol, so it's callable. It's just not documented in any of the external documentation. And so with this, you can do something very similar to the signal handler. You can register a fault handler, the same kind of situation with set jump. In your exception handler, you need to restore interrupts, or else a funny thing will happen. It works fine to restore to go back, and when I had this working initially, I was like, yay, I caught the exception, and then a few seconds later, the whole forth would come crashing down due to the watchdog timer, and the watchdog timer would complain that it thinks that you're stuck and that you never finished handling the exception. And so you need to restore the interrupt level, and if you do that, then you're able to resume back. And there's a whole bunch of different exceptions that I register for, privileged access, divide by zero, a bunch of different variants on load store, and these are all just variations based on whether you were executing the memory, whether you were loading it. There's a couple of different. The ESP32 has a very sort of weird and elaborate memory map, and so some parts of it are readable or writable or executable in different ways, and so different subset of these get triggered. And so that one actually ended up being feasible to do, and I'll demo that in a moment. And then RISC-V5 is still a work in progress, unfortunately. I've made some headway. I've figured out that there is a weird sort of a vector table that exists. It's actually not done as a series of addresses to jump to, but rather it appears to be done as a series of jump instructions, and the jump instructions are 4-byte aligned, but they're and they dispatch, unlike the Extensa chip, they just dispatch directly into the panic handler. And unfortunately, this table is not writable, but I have found that there is a weirdly a documented call that you can make that actually will reassign the location of this entire table. And so the thing I haven't gotten around to doing that I suspect will work, but I have not yet vetted it, is to create a table that accomplishes all of the same goals as this table, but for a set of the places where where the panic handler is registered that I instead wish to dispatch to my own handler, I'll need to replace them and build up something that has this exact layout and then register it with this call. So fingers crossed I will be able to do RISC-V5. Oops, this is stale from the prior iteration of this, but I do now have, well, I haven't documented yet, so, and I'm not completely sure I've gotten all the standardized values, but for the most of these, I've gone to standard µEforth throw values, and hopefully RISC-V5 will be a thing I can knock out. Let's go to a demo. And let's see. Are folks able to see that? Is that sufficiently? Actually, here, let me share that a little differently, so that's probably even better. So in µEforth,
I'll see your demo.
Great. So µEforth, I'll show this in Linux first. So I mean, the really simple thing is just if you read from 0, you get an error. You don't crash the whole forth system, which is what it would do before. And the same is true for other sort of arbitrary things. But more particularly, if you stuff this in some word, and then you run that word, and you do catch, you're able to actually catch that and get an error code, and so you can have behavior that changes based on what you do there. And the same thing is true for divide by 0. The same thing is true for stores. So if I store to a legal memory, and so I have a safety net. I can monkey around in forth, and if I get something wrong, if I do I don't know, variable x, and then I do variable x, x and store, and then it'll recover. So that's a great help, and I think will be hopefully a help to any others that are using µEforth. The other cool thing is that if I hit Control-C, it's actually triggering a fault, and so that's actually another fun thing, because it means that if I'm doing something like this, where I do a forever loop. In the past, if I ran this and it was ticking along, and now I decide, oh no, I'm stuck, before I would have to kill the whole thing, and now I can just hit Control-C and then back out at the fourth interpreter. So that a lot to get there, but a pretty useful thing. And then I'll just briefly demo this on a. Let me go ahead and actually I will. Oops. Let me fire up my. So I'm going to share a different window, and this will look relatively similar, but this is now on an ESP32. I grabbed it random in S2, sort of the same story. I get errors here. I can similarly put this in a word. I can catch it, and I still get that standard error. There's a divide by 0 and the same thing. This is nice because this is a system where it really is kind of nice to monkey around, and here I'll do. So if I load my assembler and I look at some word where I say do a disassembly of it, it's nice to be able to know that if I go and I try to store off in one of these addresses and sort of poke my way around, that if I wrote to something that I wasn't supposed to write to, some illegal piece of memory, that I have a safety net and I don't lose my state. I don't yet have a Control-C handler here. If I hit Control-C, it's sort of just ignoring me. And that's because it's a little unclear, communicating over the serial port. I don't know that I necessarily want to have it persistently ignoring a control C over the serial port, or treating a control C over a serial port as a failure, because depending on the application, that might be something that folks want to use. But please reach out to me if you have experience with sort of fourths over serial ports and sort of the right philosophy there. I do think it would be very handy to be able to have some way to interrupt the system. Maybe there's some graceful pattern where if folks intentionally are using the channel in its entirety, they would explicitly disable the fault handler. The RISC v5, one thing I anticipate will be different there. I've learned so far that on that system, actually, if you divide by 0, you get a 1, which is weird. So things to figure out. It appears that at least by default, it doesn't actually treat a divide by 0 as a trap. But are there any questions? Stunned silence. I'm going to look at the chat. I will. I see no questions.
When you use
yeah,
let me ask you something that isn't really that important, but use the dot quote. Don't put a quote at the end. Does µEforth just assume that you meant to, or?
That's a good question. I am not sure offhand. Actually, I'm trying to remember. I think it actually only goes to the end of the line. So if I do a dot quote, and I'm going to just try it here live. Yeah, it appears that it just goes to the end of the line, and the reason is that in the implementation of parse, if I'm recalling correctly, it parses either to the end of the buffer, the current translation input buffer, or it goes for the character that you've requested. And there's a little bit of a quirk in µEforth with the parse word where spaces actually get treated as equivalent to any white space, which is a little bit non-standard, but made my life easier, so I did that. But that's only if you're parsing looking for a space.
All right. If there's no other comments, I guess it's time to move on to Pig Latin. Does anyone have a solution to Pig Latin besides Brad, Bill, and Bob? All right. If you will then move along, Brad.
All right. Let me go ahead and